So yeah, thank you, Chris. And yeah, there is an element of AFM in this presentation, which will be of no surprise to you. Yeah, the main subject is how to help you prevent cryptosporidia in commercial pools, and also a little bit about energy consumption. So this is actually a repeat of the presentation I did at the STA conference back in September, if any of you guys were present there. And it's also available to view on our YouTube site. So we've got a couple of YouTube sites, and we've got one called the Dryden Pool Academy, and there's about 16 different sessions on there covering different subjects of pool water treatment, essentially. So my name's Jimmy Lamb, a fellow of the Institute of Swimming Pool Engineers, immediate past president of ISPE, and I've been sales manager with Dryden Aqua now for almost 3 years, well, 2.5 years, just over 2.5 years. What we're talking about today is, I don't like not being able to see the screen there. What is cryptosporidia, cryptosporidiosis? Have a little look at outbreak cases in the UK. I found some research online on this. I'm going to dig deep a little bit on biology in pools. The Dryden Aqua solution, and this is where I get a little bit commercial, and I apologise now, but it's very difficult to be generic when you do have products that are quite unique and don't compare with anything else on the market. So is the Dryden solution. Filtration performance, and this is really where I'm going to hone in on the energy savings that can be had, and I'll be comparing UV medium pressure systems compared to advanced oxidation systems on the market. So that might be a little bit commercial based as well, but I think you'll find it quite interesting. So what is cryptosporidium? So this is the, I need my glasses on to see that. I'm going to come around here, but you won't be able to see me. This is what I found from PUTAG, Pool Water Treatment Advisory Group. They say that cryptosporidium is a protozoan parasite that multiplies in the gut of humans and other animals. So it's not just coming from us. The life cycle stage that is shed in feces is called an oocyst. Okay, and I'm sure I'm not teaching you all to suck eggs here. Lovely subject just before lunch, isn't it? People become infected when they swallow and ingest these oocysts, and one single cell is enough to make someone ill with cryptosporidiosis. Now, this is a figure that I want you to remember. Okay, so the average size of an oocyst of cryptosporidia is roughly about 5 micron in size, typically 3 to 6 micron in size. PUTAG go on to say that cryptosporidiosis is the illness caused by the infection of cryptosporidium, and anyone can get this, especially common in young children. And the main symptoms are watery diarrhea, abdominal pain, nausea, vomiting, and a low-grade fever. So people that might swallow an oocyst when they have close contact with an infected person or an animal, and their feces, or through eating contaminated food or swallowing contaminated water. Okay, so where people become ill, there's about a 5 to 7 days incubation period. So sometimes it being quite difficult to actually trace where the outbreak has come from due to that incubation period. Symptoms usually last a couple of weeks, sometimes longer, and may come and go before full recovery. And people who have a weakened immune system are obviously could be quite a serious condition for these people, even life-threatening conditions. So did a bit of research and turned to Dr. Google, as we all do, to see what I could find, and I came across this publication, which is the Guidance for Investigation of Crypto linked to pools. Okay, it's a few years old now, but this was put together by Public Health Wales in conjunction with Public Health England. So I've just taken a few little snippets from this. And it was quite interesting, really. There's two sources of cryptosporidia. The first one, Cryptosporidia parvam. This is the one that's typically coming from animals in the environment through runoff into watercourses, enters the system in that way. And then there's the Cryptosporidia hominis, which is coming from humans. And it's this one that's really linked to recreational waters, typically swimming pools. And you can see that the largest number of outbreaks there over this period between 2009 and 2017 is accredited to This is a breakdown of the years, and we don't seem to be getting any better at managing these outbreaks, certainly during this period. In fact, quite the opposite. We seem to be seeing more and more outbreaks, whether that's through awareness and more testing and tracing, I don't know. But what else is also interesting, the month of the peak of outbreaks tends to be in the school summer holidays. August, September is when we're really seeing the peak. So people on holiday enjoying wet leisure facilities. So problems that have contributed to the outbreaks of crypto. This is a list that they outline in this document. Inadequate pool design and construction, including water features. Okay, so it's not just about the pools. I'm not quite sure about this one, sewage cross-connection. How are we getting sewage lines cross-connected with a pool plant is a curious one, so I can't really comment any more on what they're attaining to on that one. Fecal release or contamination from bathers. This is probably the biggest contributing factor, I would have thought. Excessively high bather loads. Well, we know that commercial pool operators are under pressure to increase revenue, and one of the easiest ways of doing that is to increase the bather load, get more bathers through the door. But perhaps that pool hasn't been designed to deal with such a high bather impact. Inappropriate handling and disposal of stools. So this is your emergency action plans. If somebody has defecated in the pool, how is the operator reacting to that and dealing with this situation, if they even know about it? Inappropriate response to fecal accidents, that kind of ties in with the previous one. Inadequate pool circulation, coagulation, and filtration. Obviously, this is one I'm really going to drill down on in this presentation. Filter backwashing problems. Again, we've done a lot of R&D on this particular subject. Inappropriate backwashing procedures. And then the one at the bottom there, the secondary disinfection methods, whether it's ozone or UV treatment, not working properly, not being maintained and operated properly. This is really a belt and braces to give protection against cryptosporidia. In section 3 of this document, they talk about swimming pool water treatment and quality. Okay, so here they're 3.1 basic principles of swimming pool water treatment, disinfection, and efficacy against cryptosporidium, because we know that the oosysts of crypto is a very hard-shelled parasite, and is immune to even very high levels of chlorine. It takes a long time for chlorine to break down these pathogens. Bathers and bather numbers, there's some guidance there, and swimming pool design, circulation, and filtration, okay, which is our speciality. And what's really interesting in the summary of this document, as I've highlighted there, is the best way of dealing with an outbreak, once you know that there's one there, the removal of these oocysts from pool water really relies on good circulation with optimal filtration, coagulation, and flocculation. Okay, so I'm going to go back now and have a little think about the biology in swimming pools, rather than the chemical side. You know, for many, many years, we've always very focused much on the chemistry of a pool. You know, we know we have to add a chlorine, we know we have to balance the pH, and we know we have to maintain good water balance through other means, other parameters. But for us, really, the heart of the system is good circulation and good filtration. Without that, you're really fighting an uphill battle. So we're starting from looking at pool water treatment from a biological perspective, and this is really the heart of Dryden Aqua. The company was established by marine biologists. So how do bacteria survive in a pool? There's never a bacteria-free pool. It's never a sterile environment. There's always a level of bacteria present. And the indication of how effective our treatment regime is how we're able to manage the level of bacteria that's allowed to proliferate in a pool. And the guide for that is by doing a monthly microbiological tests, yeah? And if the count comes back within acceptable levels, we know we're okay. But this bacteria that's existing in the pool will be of different of a different resilience. Some will be destroyed in a matter of seconds by the oxidizer in the water. Others will have a stronger resilience, and what they're striving to do is to reach and touch a surface. Once they've found that surface, they'll then excrete an alginate around themselves. And this is the early formation of biofilm production. So they're now within this sticky substance that we call biofilm on that surface, and it's now protected and safe from the chlorine in the system. Even chlorine as high as 50 ppm, yes, it will oxidize a lot of the biofilm, maybe 99%, but we've still got that 1% of bacteria growing within a biofilm. You know, you see the adverts on telly for your Domestos bleach, kills 99.9% of germs. There's still that little bit of germs left in the system, and it then starts to grow a resilience to the oxidizers in the water, and we can get the formation of superbugs. I liken it to the antibiotic effect. You know, if you've been unfortunate to get some kind of infection and you go and see the doctor and he prescribes antibiotics and he tells you, please finish the course. It might be a 5-day course, a 7-day course. But that infection might have gone within the first 3 days of taking that course. And you feel like, well, it's gone, I don't need to continue taking the antibiotics. But there will be a little bit of that infection still there, and it will grow resistance to those antibiotics. And you get the formation of these super germs. So, digress somewhat there. Come back to pools. The bacteria in a pool. Okay, so it's found a surface to stick to. It's now safe inside the biofilm. It's a nice warm environment with plenty of nutrients being introduced to the water from bathers. So it begs the question, where are the available surfaces within a system for bacteria to grow? Well, my first answer to that question many years ago was, well, it's the pool tank, isn't it? You know, this is a huge surface area. The walls, the floor, and where the water's being held, where people are swimming. On face value, absolutely. And this is why it's really important to make sure that we brush the walls, brush the floor, perhaps with an automatic cleaner, to keep that free of bacteria slime. What about the pipe work? These are areas that we can't get to. It's really quite difficult to get to the pipe work and clean the pipe work. So this is where chlorine dioxide treatments come into their own, because we know chlorine dioxide being a soluble gas, this will penetrate and remove a biofilm from the surface that it's stuck to. So perhaps good regular maintenance checks with a chlorine dioxide treatment to keep the pipework clean. But really the largest surface area that's available for bacteria to grow is in the filter media itself. Every grain of sand has a developed surface area. And if you multiply that up, if the filter's been sized correctly, that will represent well over 90% of the total surface area that the pool water's in contact with at any one time. And this kind of makes sense. You know, this is why we start to get the mud balling and biocoagulation typically in sand filtration. This is where we're trapping all the particulate matter, hopefully, and all the nutrients within the filter. So it's the perfect breeding ground for bacteria. And we know that Cryptosporidia can find its way into a biofilm and be safe in there, and it can disperse from that biofilm at any time. This isn't something that happens overnight with sand filtration. This takes time for the bacteria to develop and grow and produce the biocoagulation and the mud balling that occurs within a filter. And under pressure, the water's trying to pass through that media, and it will start to push the mud balls to the side, and the media bed will open up, and we get channeling, wormholing, and the debris that we're trying to trap will eventually just pass through the filter. And occasionally we can get these biocoagulation anoxic zones rupturing and releasing bacteria into the water as well, into the flow of the water. So this dissipates any chlorine residual that's present in the pool very, very quickly. So the turbidity of the water increases. The chlorine consumption increases because we've basically got a biofilter here. We've got a filter media full of bacteria. So this is consuming the free chlorine. And this filtration is no longer reliable. This is a good example of wormhole channeling. This is a high rate filter in a domestic setting. And if you've ever had the pleasure of going out and doing a media change, you might relate to this picture. Particularly when you get down to the bottom of the filter, around and underneath the laterals, it can be pretty unpleasant. This is biofilm. I do like the use of PPE gear in this in this picture. I hope he washed his hands thoroughly before he went on his sandwiches for lunch, because yeah, there'll be all kinds of nasties within that little mud ball there. So how can we help to prevent crypto? We saw at the beginning that circulation and filtration is really the best way of dealing with cryptosporidia. So this is the part where I'm sorry, I'm going to get a little bit commercial, because it's our solution to help prevent crypto. And the reason why I say it's commercial is because they're unique products that we're putting together into a system. And the system, we call it, is the DAISY system. This stands for the Dryden Aqua Integrated System. And it's utilizing a filter media that's produced from green and brown glass up in our facility in Edinburgh. And the result of our production methods is that it makes it 100% bioresistant. So bacteria physically cannot reach and touch the surface of this glass media. So we literally take bottles from the bottle bank, so that the more bottles of green and brown beer that you drink today, the more raw material we've got to make this media from. We basically take it and put it into a hopper at the beginning of the process. Now you can imagine we get an array of other material that we don't want. That includes clear glass that doesn't make for very good filtration. But we also got the labels to remove. We've got the enclosures, whether they're plastic, ferrous and non-ferrous. This all needs to be removed from a process of magnets, blowers, suckers, eddy currents. The factory in Switzerland is powered 100% by solar power. Unfortunately, we don't have that luxury in Edinburgh, but we do have an element of solar production there, but not to the extent that we do in Switzerland. We then wash the raw material with harvested rainwater. We've got enough capacity in Switzerland to have water for 3 months. So if it doesn't rain for 3 months, then we need to tap into the mains. That's on a sustainable loop as well. The dirty water is then filtered with our own technology, and we reuse that. Everything that we consider a waste product gets repurposed. I mentioned clear glass, for example. We've just invested another 2 million up in the plant in Edinburgh to remove clear glass, because 50% of our raw material is clear glass. We don't want that. So that goes back to making whiskey bottles or medicine bottles, for example. Ceramics go to different industries. Even the sludge from the cleaning process goes to producing biogas. So we try and have a zero waste policy as much as practically possible up there. This is coming back to the roots of Dryden, the marine biologist philosophy. The final process, not the final process, it then goes through a sterilizing process because we still get some loose organics coming through the system. So we burn these off and clean this at the end, and we end up with less than 10 grams of organic contamination per ton of finished product. Why do we want green and brown glass? The reason is because the metal oxides that give the glass that colour already has a natural bioresistance. So in the case of green glass, this is a chromium oxide, and brown glass, it's ferric oxide. So we're just enhancing that natural bioresistance through very sophisticated machines, and in a nanosecond, this machine is identifying the size, the shape, the transparency of the particle, and with a jet of air, it's sending it off to the relevant conveyor belt. And it goes through this 2 or 3 times before we end up with the right colour selection. We then put the material through what we affectionately call the beast, and the beast is producing the right shape and size of the various grades that we're producing. Typically grade 1, 2, and 3 for use in swimming pools. Grade 0, which is quite a fine grade, is used in more water treatment processes. And then this is where the magic happens. This is the top secret process of our manufacturing process, and it's a 3-step chemical and thermal curing process. You can witness this. This isn't something that happens behind curtains. You can actually visit the factory and witness this process, but we don't tell you what the magic ingredients is. I don't even know what it is. There's probably about 3 or 4 people within the company that know what that formula is. It's a bit like your Kentucky Fried Chicken or your Coca-Cola. And they can't share a car or get on an airplane together. You know, it's that kind of secret. But it's this process that gives us a resulting factor of a 100% bioresistant material. We then have a very strict quality control procedure, so the computer at random, with every batch that's being produced, will select the bag, send that through to QC, and they just do some checks on it to make sure it's still being produced to our specification. And this is all traceable. Every bag is barcoded, every batch. I think independent verification is really important as well. So we originally turned to German DIN to see if we could get some kind of certification from them, and they pointed us in a direction to this laboratory in France, the IFTS laboratory, the Institute de Filtration Separatives, or something like that. That was my best French, by the way. That looks quite a complicated chart there, but if we look at the bottom here, if we go to the bottom here, this tells us that 95% particles removal down to 1 micron. This is at a filtration velocity of 20 meters an hour. So we're in the realms of commercial filtration velocities. PUTAG standards allow us to go up to 25 meters an hour. So what's 5 meters an hour between friends? So yeah, AFM is removing 95% of particles down to 1 micron. This is probably a bit easier to understand. This is the, along the bottom axis here, this is the size of the particle, and the left-hand axis there is the percentage of removal at 20 meters an hour. And if we draw that line of 95% particle removal, you can see that AFMNG is down to 1 micron. The next best performing media in these tests was actually a sand product from the old Leighton Buzzard pit, which has since been depleted. Another example as to why sand is an unsustainable solution, destroying habitats. It filtered at 20 micron. This is when it's clean and brand new. So over time, with biocoagulation, this will start to deteriorate. And then you can see some other squiggly lines there. This represents other different suppliers of glass filter media. A new standard European norm, British standard, that was published at the end of 2024, BS EM 17978, is a quality standard. So this isn't a performance standard, this is a quality standard for products used for water treatment intended for human consumption and swimming pool water, glass beads and granulate. You need sophisticated equipment to make sure that your product is within these parameters that this standard is set on. And the first one there is the organic contamination. You're allowed up to 300 grams per tonne. Ours is 10 grams per tonne, so we're well within that limit. The other one is magnetic contamination, up to 50 grams per tonne. But I think the interesting one for us is the over and undersize of each grade that you're producing. So for the filtering grade, you've got a tolerance of 5% there. So if we say our media is 0.4 to 0.8 millimeter in size, you've got a 5% tolerance to that figure, and 10% for the support grade, so grade 2 and grade 3. You do need sophisticated equipment to be able to measure this to get your S curve on that size, and that comes at a cost. I often get asked the question, how long does it last? Well, this May will be 22 years that AFM has been in situ at the Leisuredrome in Bishopsbriggs, just outside of Glasgow. And that's the technical guy there who's been there all that time as well. He's a rare breed. You don't see technical guys too often in big commercial pools anymore. But I visited there a couple of years ago, did some analysis on the turbidity of both incoming and the pool water, and it was as good today as it was 20 odd years ago, so it's still performing really, really well. you can clearly see there that it's a very well-dimensioned, very generous dimensioned plant as well. So we've got good flow efficiencies, not just for filtration, but for the all-important backwash.
Running a
We do like a movie at Dryden Aqua as well, so I won't play that just now, but you can visit our YouTube sites to glean more information that way. So DAISY offers for us a great solution to help prevent crypto, purely because of the filtration properties. That 95% of particle removal down to 1 micron. So that figure I asked you to remember at the beginning, the Cryptosporidia oosysts, typically around about 5 micron. We are creating a barrier to that with a well-dimensioned filter. And because we're not growing the biofilm within a filter, there's nowhere for those oocysts to hide within a biofilm as well. Step 2 to make this a DAISY system is the introduction of coagulation flocculation. Okay, so we produce our own called APF, all polyfloc. And this isn't an exact science, but broadly speaking, when you use coagulation flocculation, you improve the filtration performance by a factor of 10. So this is how we derive at the 0.1 micron. We are talking to IFTS in France to see how we can get this verified by them as well. So watch this space on that subject. APF is PAC based, but there's other ingredients in here as well, such as lanthanum. And if we add lanthanum to the pool water, we can remove phosphates, which again is a nutrient for bacteria and algae. So again, trying to reduce the chlorine demand on the system. So with DAISY, AFM and APF, the best filtration down to 1 micron, creating that barrier. Giardia is another one I never mentioned at the beginning, but everyone seems to be very focused on crypto, but Giardia, not quite as resistant to oxidizers like crypto, but can still cause some pretty severe upset stomachs. So if you size it properly, the benefits of a DAISY system, potential to filter down to 0.1 micron, so we're into the field of ultrafiltration. We create that barrier on a single pass to Cryptosporidia. We reduce oxidation demand by up to 80%. Clear and safer water without the pathogenic bacteria. Healthier air, so we're not producing trichloramines and THMs. I'll come on to that in a second. And overall, lower operating costs. We're typically using, in our experience in the UK, we're typically reducing backwash duration by 50%, which equates to 50% less water consumption during the backwash. So let's come back to biological matter, shall we say, and some of these chlorine byproducts that can be produced in a pool. Biofilm is responsible for the formation of trichloramines. So when we're submersed in nice warm water, whether we like it or not, we are excreting substances from various orifices. It's lovely, isn't it, just before lunch? Okay, so we're sweating, we're maybe giving some urine. They reckon that in a couple of hours in water, an athlete can secrete up to 1 litre of sweat and 80 ml of urine. Now that substance is made up of amino acids, creatine, ammonia and urea, but it's largely urea. About 80% of that substance is urea, which is the perfect nutrient for bacteria that's living within a biofilm. If we have a filter media that's resistant to biofilm and we're preventing that 90% of surface area from growing biofilm, the urea will remain, sorry, bit of a tongue twister. The urea will remain urea, but it will still react with the chlorine in the water to form a chloramine, but it's an organic chloramine. It's pretty harmless. It's when the urea is absorbed by bacteria living in a biofilm, they metabolize it and then secrete ammonia. And it's the ammonia that becomes the problem. It then reacts with the chlorine and we get inorganochloramines in the form of monos, dies, and the volatile one, trichloramine. But DPD number 3, DPD number 3 to your DPD number 1 doesn't differentiate between the two. It's measuring the sum of organochloramines and inorganochloramines. Okay, so what we don't promise is a reduction in your combined chlorine. It's a reduction in your trichloramine production. So you don't get that horrible chlorinous smell in a pool hall anymore. It irritates the eyes, nose, and throat. But you can still get combined chlorine showing up on your DPD3. Any questions so far? Good. Yeah, it might be a good idea.
Everybody else can hear.
Oh, okay.
Right.
Yeah, thank you. It's Duncan Ockenden. I was asking, are you saying, Jimmy, that trichloramine is only formed through biofilms, or is there no chemical route through for the formation of trichloramines?
The majority of trichloramines are produced when we've got heavy bacterial colonization of a filter media. One slide I've left out on here is the pH range where trichloramines are formed. So if you're operating your pH in your pool between 7 to 7.6, hopefully within the norms, you'll still produce monos and dies. You still get a reaction of monos to dies. But to actually get to that third stage transition to trichloramine production, you do need quite acidic conditions. So where the acid injection point is, perhaps, we would get a transition there to trichloramine production. But the substance that biofilm is produced is actually a very, very acidic condition. You need about pH 5.5 to get to the transition to trichloramine production. So if you've got heavy contamination of biofilm in this system, which is very acidic, you've got perfect conditions to transit directly to trichloramine production. Does that answer your question? I'll wait for the microphone.
Hi there, my name's Ed from Kindling Sauna. We're looking at developing a shower reuse system to be able to make the water clean again for showers for our saunas. Could you use your, is it Daisy, the green brown glass compound, instead of sand in the filtering for that, or do you need to buy your entire system with all the different parts?
No, that's the beauty of the AFM. It is a direct replacement for sand. There's no need for investment in infrastructure, for reinvestment in infrastructure. Yeah. Okay, so just a little bit now on the energy saving side, and this is mainly on the use of different UV technologies. So just comparing medium pressure UV with other systems available on the market. Reduction of combined chlorine with medium pressure UV. So this fancy graph that you see here is the blue line, the long wavelength, if you like, of medium pressure UV shows that it will reduce free chlorine, which is the red line, by an amount. So any free chlorine that's passing through a medium pressure UV system, the free chlorine will get neutralized. The green line is the free chlorine at a pH of 7. Medium pressure UV systems need a lot of power. They're quite energy hungry to produce that broad spectrum of light. The black line that you see in the middle is of a low pressure UV system. This doesn't have the power consumption, but it's a much shorter wavelength of UV light. Now, what is the purpose of having medium pressure UV on a pool? Why do PUTAG recommend medium pressure UV? They recommend it for good reason. First of all, medium pressure UV is excellent at removing combined chlorine. And that's what we can see here on this graph. So this is the medium pressure wavelength again. Sorry, I'm away from the mic, aren't I? And you can see that the green line there, which is the trichloramine, the volatile one, the undesirable in pools, is actually taken out very effectively by the wavelength of the medium pressure system. It will also take out monos and dis as well, compared to the low pressure, which is barely touching it. Yeah. Did you have a question? No? Sorry. Medium pressure UV breaks large organic molecules into smaller ones, which then react to THMs, trihallomethanes. So what do we mean by this? I mentioned that we're still producing organochloramines in the system. There's still organic matter in the system rather than the inorganic matter. An organic molecule is an organic compound made up of hydrogens and carbons. And through the process of oxidation, this molecule is chopped up into smaller molecules. Methanes, where you've got one carbon and 4 hydrogens. With the chlorine in the water, we get an exchange, an atom exchange of the carbon, of the hydrogen to the chlorine to form a chloromethane. You then get a further exchange to a dichloromethane. Guess what's coming next? Trichloromethane, THMs. This is chloroform. And through agitation of the water, this can be released and given off into the atmosphere. And it's an odorless gas, really. So you wouldn't necessarily know it was there, and it's not monitored or regulated in this country. An alternative to a medium pressure system is advanced oxidation, which offers a complete oxidation of organics in the system. So advanced oxidation is utilizing a very high dose of UV radiation, but with low pressure lamps, typically 5,000 joules per meter squared. And it's acting as a catalyst to the introduction of hydrogen peroxide through the bypass on a loop. So it's a slightly more complicated installation because it's on a bypass. You need a flow meter, you might need a boost pump on the bypass, and then you're bringing in another chemical, hydrogen peroxide. But when you split the hydrogen peroxide molecule, you create hydroxyl radicals. These have got a very high oxidation potential, higher than any other substance, but they're very unstable, they're very short-lived. But any organic contamination within the vicinity is 100% destroyed. It's what we call a complete oxidation process. So we're not producing those methanes to then become dichloromethanes and trichloromethanes. So yeah, this is like a Star Wars picture or something like that. So there's the high dose of UV light reacting with the hydrogen peroxide, creating the hydroxyl radicals that then destroying organic matter within that chamber. These kind of systems will remove all manner of substances that you wouldn't even know were present. And I'm not even going to try and pronounce some of these substances. But it really does give for excellent water quality. So why is advanced oxidation better than medium pressure UV? Medium pressure UV are generating THMs and consuming about 50% of the free chlorine. You will lose some free chlorine as well with the advanced oxidation systems, because not all of that hydrogen peroxide is going to get converted to hydroxyl radicals, and that will have a neutralizing effect on the free chlorine. So you will lose a little bit of free chlorine as well. Medium pressure UVs are expensive, or more expensive, should we say, in CapEx and in OpEx. They're power hungry, as I've already mentioned. They generate heat as well, so maintenance of them can be higher, potential scaling up of the quartz tubes, and the lamps tend to have a shorter life expectancy. So I did some analysis on costs, and I went to 2 installers of medium pressure UVs in the UK market and did a comparison based on a pool of 500 cubed. So the capital cost of each of the systems, so just over 17,000 for the medium pressure compared to just over 11 of the advanced system. and we put the installation costs down at the same, just to give it a level playing field there. That includes ancillary products like that you need a dosing pump for the advanced system. Lamp sizes, quite different here. So 3 kilowatt lamp for the medium pressure compared to 300 watts of the Advanox system. Commercial cost per kilowatt hour, I don't know, 26p, it's around about that, I think. And if the lamps were running 24 hours a day, then this would be the running cost per day for each of the systems. So quite significant difference there. And if you multiply that up for the year, again, it's a significant difference in the costs. Life expectancy on this system was 9,000 hours compared to the 24,000 hours because you actually get a spare set of lamps with the advanced system. So we equated that to the number of lamps per year, big difference there, and then the cost of service and spares, similar but still quite different. Of course, with the advanced system, we need to take into account the consumption of hydrogen peroxide that's required to run this system. And in this particular pool, that would be the dosing rate. And there's typically two different strengths of hydrogen peroxide available. So I went to the largest supplier of chemicals in the commercial pool market and got their costs and the volume that they would need depending on the strength. In this example, I've gone with the stronger strength because the commercial pool operator wouldn't need a license to secure that product at the higher strength. So the additional cost per year just for the hydrogen peroxide in this example is just under 600 quid. So it's pretty insignificant in the grand scheme of things. Now, if the two systems are running side by side 365 days a year, the capex, including installation, is very different, as are the running costs. And if we cut to the chase down to the bottom line, in the first year, the overall savings are significant. That's capex and opex in the first year. But then, of course, every year, it's going to be saving £5,500 just in running and maintenance costs. So it's quite significant. So for us, the best solution is DAISY, to create that barrier to protect yourself against cryptosporidia. We filter out efficiently, we backwash it out of the system, we allow it very little hiding place in the system to hide in biofilms. We use coagulation, flocculation to improve the filtration efficiency, and then we take care of the combined chlorine, which is more strictly regulated than a lot of our European partners. For example, Switzerland, the highest level of combined chlorine there allowed is 0.2 milligrams per litre. You know, what are we here in the UK? No more than half that of your free chlorine with a maximum of 1. So worlds apart. So it can be really quite a challenge for some of our European partners to manage that. So we can manage that effectively with Advanox. You can also use a little bit of activated carbon across the filter if you wanted to as well. There are other solutions. A better solution and healthier solution than a public pool indoor with medium pressure UV, and as good as a public pool with ozone, because ozone has always seemed to be a very good solution, but very expensive again, temperamental, and requires a lot of care and maintenance. As I said at the beginning, all of these sessions, including the one I've just done today, are available on our YouTube site, the Dryden Pool Academy. We've got 16 sessions on there now, covering various subjects of pool water treatment. So it just leaves me to say thank you very much for your time and your attention to come and see me. And do you have any questions?
Thank you. Jimmy, it's me again, Duncan Ockenden. I have two questions. One is, with your example with medium pressure UV, you talked about, I think, a 500 cubic meter pool. Would that be, say, a 25 meter pool? Can you Can you explain why variable power control hasn't been taken into account in your power consumption estimate of 3 kilowatts?
Yeah, no, I've just used that example of both systems running 24 hours a day on full power. I appreciate that. In fact, we're working on a system called SPACE now that will measure both free and total chlorine to calculate the combined. And that can then be used to switch on and off or ramp up and down the power of a medium pressure UV system to help save the energy consumption. And I know that there are other systems out there that do that as well.
Significant effect on operating costs.
Of course, yeah.
Yes. And the second question is, on what scientific peer-researched evidence are your claims that medium pressure UV is a net creator of trihalomethanes based?
It's a case study that we did in Holland. It's in one of our publications.
This was a case study run by Dryden Aqua.
No. It was an independent laboratory done with our distributor, in partnership with our distributor in Holland.
And are Dryden Aqua actually manufacturers of UV systems?
We've partnered with a Dutch company again called Van Riemen. You might be familiar with them.
Low pressure UV?
Yes.
I know them well. Okay, I would query many of the findings that you presented, but anyway, thank you.
Yeah, sure.
Okay, have we got any other questions? I'll come to you with the mic.
Jimmy, mine's an easier question. The purchasing of AFM, can that be done direct or is that through distributors?
We work through 3 distributors in the UK now. That's Golden Coast, Astral and Certicon, who are all here this week.
Thank you.
Any other questions? No, I think Jimmy deserves a round of applause. Very good presentation. Thank you.